Okay, so in this video, we're going to start talking about significant figures, which is usually the one thing that you either understand easily, it's not an issue, or it's the one thing that's going to stump you for the entire semester. So here we go. So first of all, when we're talking about significant figures, the big important part about significant figures is measured numbers. Yes, there's significant figures when you're doing calculations, but the important part and the part that I am picky about is that you're using good data. When you're in the lab, I expect you to use good data. I expect you to be taking good measurements. I expect you to be rounding correctly. I expect you to be reading your instruments correctly. And this is the concept of significant figures. Now, measured numbers are numbers that are written when you measure any sort of quantity. In the lab, we call this data. This is really important when you're recording data, because when you write down an answer, you're telling me your answer and you need to be communicating it with me correctly, and not just with me, but with other people. If you have $167 in your bank account, you want all $167. You don't want somebody to say, "Oh, I have 150," and just give you 150 and pocket the $17. If you have $167, you want your $167. Okay, the same principle applies when you're communicating data with me. It needs to be communicated correctly. If you have 1.5 centimeters of something, you need to tell me it's 1.5, not round it to 2 or round it down to 1. You need to tell me 1.5. It's important. So when you are reading an instrument, you need to read all the lines that you can see, and then you need to estimate one more. And I'm going to show you an example here in just a second, but you always read what you can, and then you guess one more. The data can only be as accurate as the instrument. If your instrument is not very accurate, then your data is not going to be very accurate. So this is an example I always like to use because you guys are familiar with this. Gas is priced incorrectly. So for instance, I'm not sure what the gas is today, but the other day it was $1.89.9. Now, our currency does not allow us to have a thousands place right here. We have down to the penny, so I can tell you something is $1.89, or I can tell you something is $1.90, but I can't tell you it's $1.89.9. This amount is more accurate than our monetary system is. We can't go back, we can't get exactly 1 gallon of gas and go in the gas station and tell them we want our tenth of a penny back. No, they're going to charge you $1.90. And so for them to advertise $1.89.9 is kind of pointless because our monetary system is not that accurate. We cannot physically pay $1.89.9. So we all know that when they do $1.89.9, that it's actually going to be $1.90 per gallon, because again, we can't use that specific of a measurement in our currency. So here's what I mean. Here we have 3 different rulers. Okay, if I ask you guys to take a pick as to which one is more accurate, I'm hoping that most of you are going to tell me that this ruler is more accurate because we have all of the tens places marked there. Okay, versus these who don't. So this is what I mean by what I said in the previous slide, how you read the lines on your instrument and then you guess one more. So let's look at the first one. Okay, so if we're looking at this one, we can see that it is 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters, 5 centimeters, but I don't see anything in between. And so if we're looking at this stick and you guys are trying to tell me how long it is, I could say it kind of looks like it's about halfway between 4 and 5, right? So I would write down 4. I'm reading the lines that I can read. I can read the 4, so I write down the 4. And then I estimate one more. And so I'm going to say that that's probably 4.5 centimeters. The 4 I was able to read. The 5 was estimated. Now, most of you would agree that if you told me that that was 4 centimeters, you would be like, and I counted it wrong, you would understand why I would count that wrong, because that is clearly not 4 centimeters. If you guys wrote down the answer of 5 and I counted it wrong, most of you would understand, because you can clearly see that that is not 5 centimeters either. You can see that that's 4.5. So when you're taking data in the lab, I expect you to write down 4.5 in this situation, not 4 or 5. Okay, so now let's look at the next example. This one is a little bit more difficult for you guys to see. Now, again, We write down everything that we can read and we guess one more. So this is the same exact stick from earlier. We still see the 4, and not only do we see the 4, but we can now see the tens places. So we can see that there is 1, 2, 3, 4, 5. We can see there are 5 tens places here. So I can write down now 5. This is the one that we were read. This one we were also able to read. Now remember, the rule is you read all the lines that you can read and then you estimate one more. I read the 4, I read the 5, I need to estimate one more. And if we look, the stick is not exactly, it's not exactly on the 5, and it's also not exactly on the 6. So we're going to estimate one more, and to me, that looks like it's right smack dab in between. So when you're communicating this data to me, you would write 4.55. This one is estimated. Now, up here, we wrote that it was 4.5. And you guys understood why 4 was wrong, and you understood why 5 was wrong. And so you guys would have most likely given me 4.5. But on this one, you guys, if you guys wrote 4.5 and I was expecting an answer of 4.55 and I counted it wrong, a lot of you would be like, that's such a small difference. Why are you counting that one wrong? That's only a hundredths place off. And my answer is, well, I'm making sure that you know how to read your instruments correctly. I'm asking you to do it a specific way. You're communicating that you're able to read your instrument, and it's basically, I'm just trying to make good habits. Am I going to get super mad if you don't write down the hundredth place? No, but I want you guys to be learning how to read your instruments correctly, and so it's a learning process, so I am going to expect you to do that one more estimation. Okay, so let's look at number 3 while we're here. Now, this is 3, right? Remember, we read everything that we can, and then we estimate one more. So this one, we can read that it's on the 3, but most of you can agree that that's exactly on the 3, right? Well, how do we estimate one more when it looks like exactly on the 3? Well, this is where our zeros come into play. Zeros are very important when we're doing significant figures. This 0 is estimated. This one is the one that we're reading. And that 0 tells the person that that is exactly on the 3 as you were reading it. So if you just write a 3, is it a little over 3? Is it a little under 3? Is it exactly 3? Who knows? But when you write 0.0, it tells the person that that is exactly 3, that your measurement is exactly 3. Now, that's how we measure using a ruler. Now let's talk about a graduated cylinder. This is a graduated cylinder. And when we have a graduated cylinder, there's something called a meniscus line. So if we look at this, we can see how it's starting to curve down right here. Okay, that's called a meniscus line, and it's very, very important that we read the meniscus line. In order to read the meniscus line, you have to kind of get eye level with it, and you want to read the bottom of the curve. Now, we can see that these two liquids look approximately the same, but remember, when we are taking measurements, you read your instrument and then you guess one more. So when we're reading this graduated cylinder on the left, we can see that it's above the 4, so that means that I can write 4. This is the one that we are read, and then I need to estimate one more. So it's between the 4 and the 5, and not only is it between the 4 and the 5, but it's closer to the 5 than it is to the 4. So my guess would be 0.8. 4.8. This one is our estimated one. Okay. Now, if we use the second graduated cylinder, we can see that this is a more accurate graduated cylinder because it has the tenths marked over there. So again, now we're going to read all the ones that we can read. So we can still read the 4. And then we need to count. So it is at the 1, 2, 3. It's at the 1, 2, 3, 4, 5, 6, 7. It's above the 7, but only slightly above the 7. So I can read the 7, and then I need to estimate one more. So this one we were able to read. This one we were able to read, so I need to estimate one more. It was only a little bit above the 7, so I'm just going to give that a 1. So 4.8 versus 4.71. It looks like a small difference, but it's actually relatively important that you measure using this way. Because in the lab, several of our experiments you're going to have a mass difference of maybe a hundredth, maybe a tenth. So it's very important that you're taking accurate measurements. Okay, so now this is the part that most of you have the most trouble with, is determining significant figures, but it's just a series of rules, and it's basically to make sure that you're calculating your data correctly. So, like I was giving you with the example of the 3, sometimes we have to show our accuracy with the use of zeros, like we had to write the 3.0 so that you were communicating that it was exactly 3. So here's a few rules to kind of help you do that. First of all, when we are talking about significant figures, all digits 1 through 9 are significant. They cannot be omitted. We cannot throw them out. They're very important. The ones that come into play are zeros. So first of all, if a 0 is in between 2 digits, this is called a sandwich 0, they are significant. Trailing zeros, zeros after a number, are only significant if there is a decimal. So 23.0 or 340.0, all of these zeros in these two numbers are trailing zeros, and there's a decimal. So this 0 would be significant, and both of these zeros are significant. However, these zeros are not significant because there's no decimal. 630, that only has 2 significant figures. That tells you that this number has been rounded. When I write 630 like this, the actual answer was anywhere between 625 and 635. It has been rounded, and that 0 tells me that I have a 10 number range here of accuracy, which isn't very accurate. If you have $635 in your bank account, you don't want somebody just giving you 630. You want $635. And so zeros are a way to communicate accuracy. And then leading zeros, these are zeros that are found before numbers. These are never significant. They are literally just placeholders trying to give you, usually to represent really small digits. Now, let's practice a little bit. So we have some leading zeros. Leading zeros are never significant. Then we have 4, 6, 7. Numbers are always significant, but then we have a trailing 0. So we need to come back up here and we need to look. Trailing zeros are significant if there's a decimal. This number contains a decimal, so that 0 is significant. So that gives us 4 significant figures. Okay, the next one, we have a sandwich 0, which is significant, and a trailing 0. Trailing zeros are, again, only significant if there's a decimal. There's no decimal, so this 0 is not significant. So that gives us 4 significant figures again. And then the next one, we have 2 sandwich zeros, which are always significant, and another trailing with a decimal. So all of these digits are significant, so we're going to have 6 significant figures in this one. Now, this sounds a little silly, but this allows us to calculate things accurately, because most of the time when we collect data, we then do calculations on it. The first couple of labs we're going to be doing density. So when we're doing with significant figures, we have a few exceptions to the rules. Now, it doesn't matter if I walk around this room, if I'm in a classroom and I walk around the room and I have 12 students in the room. It doesn't matter if I write it as 12 or 12.0 or 12.00 or 12.000. It doesn't matter how accurate I am, because 12 people is 12 people. You can't have half a person. So counted quantities do not have significant figures. Okay, conversion factors do not have significant figures. There's always 12 inches in a foot. It doesn't matter if I write 1 foot or 1.0 feet or 1.00 or 1.000. 1 foot is always 12 inches. So those also do not have significant figures. And another thing that also does not have significant figures is accepted information, such as density. If I give you the density value and you're using it in calculations, you don't let that affect your answer. If you're looking up the atomic mass off the periodic table, those numbers do not affect your significant figure in your calculations either. So let's do some practice with calculations now. Significant figures are very important in calculations because we usually are going to do calculations with our data. Now, where this comes into play is your final answer can only be as accurate as your least accurate data. So I always like to say you're only as strong as your weakest link. So if one of your data is not very accurate. They were using one of those rulers without the tenths mark. They were using a thermometer that didn't have degree markings on it. That data is not very accurate, so when you use that data in calculations, you can't automatically, just because your calculator spits out an answer with 50,000 decimal places, that doesn't mean that your answer is that accurate. So when you are recording your answer, you have to make sure that the accuracy of your answer is the same accuracy that you were given in the lab. So we're just going to do a few examples. So when we are doing calculations, there's two different types of computations that you're going to do. You're either going to do multiplication or division, or addition and subtraction. When you're doing multiplication and division, your answer has to have the same number of significant figures as your least accurate answer. So if we look at this, we have 24.2, which has 3 significant figures, versus 3.1, which has 2. 2 is smaller than 3. 3.1 is not as accurate as 24.2. So when we do this calculation in our calculator, when we do 24.2 times 3.1, my calculator tells me that the answer is 75.02. This has 4 significant figures. This has more significant figures than any of our data, which isn't possible. We cannot be more accurate in our answer than our data is. So the rule says that we can only be as accurate as our least accurate. This one only has 2, which means our answer can only have 2. So we're going to have to round. Rounding, if it's bigger than 5, we round up. If it's less than 5, we round down. So we have to look at 0. 0 is less than 5, so this would get rounded to 75. So we would record our answer as 75 because our least accurate answer only has 3.2. Now, when we are adding or subtracting, the rule changes a little bit. This time we have to look at our number of decimal places. So 24 has 0 decimal places, whereas 1.4 has 1 decimal place. So when we put this in our calculator, if we do 24 plus 1.4, we're going to get 25.4, which is more accurate than our first answer. This answer over here that has 0 decimal places, this person wasn't using a ruler with the tenth marks marked. So 24 is rounded. The answer is anywhere between 23.5 and 24.5. So our answer cannot reflect that, so we're going to have to round. We can't have any decimal places because that answer doesn't have any decimal places. Since 4.4 is less than 5, it's going to get round down, so we would round this as 25, and this would be the answer you would communicate in your data. Again, significant figures are difficult. It's going to take you guys a while to grasp it, but after a while you'll kind of get in the habit of it. So let's do a little bit of practice. So first of all, let's practice reading data. So remember, when we're reading an instrument, you read the lines you can read and you estimate one more. So let's look at our thermometer over here. We can see that there's a 20, we can see that there's 30, and these are your tenths marks. The line looks to me like it's just a little bit, it's in between 2 lines. So we have 20, 1, 2, 3. So this would be 23 degrees. And then that's what we can read. We need to estimate one more. And that looks to me just to be right smack dab in the middle. So I'm going to write 23.5. This one is estimated. These are red. I will count you off in your labs if you are not taking accurate measurements. Everybody in this class can read an instrument correctly. Okay, if you cannot do calculations with significant figures correctly, that's one battle that I will help you with in class. I do expect you to be able to read your instruments correctly. So, the next question, how many significant figures are in this? We have a sandwich 0, which is significant. We have a trailing 0 with no decimal, so it's not significant. So this would only have 4 significant figures. Okay, and now let's practice doing math. In order to do this, because we have both multiplication and addition, you have to remember your order of operations. You do multiplication first. So I'm going to do the 3.46 times 2.1, and I get an answer of 7.266. But when you multiply, our answer can only be as accurate as our least accurate. So this one only has 2. So we would only be able to write 7.3 down. Okay, 21 times 1.2 gives us 25.2. Again, we can only be as accurate as our least accurate. This guy only has 2, so I would have to round this to 25. And then we have to add them together. Adding, we have to look at our number of decimal places. So 7.3 plus 22 gives us 29.3. But since 22 has no decimal places, I cannot keep that 0.3. Since 0.3 is less than 5, we get to keep it as 29.